Hi everyone, welcome to eMemory's webinar today. My name is Wei Chen. I am a department manager at the eMemory Technology Department 5 and joined eMemory 10 years ago. I am glad to introduce our new embedded logic multi-memory solution for AI chip application. First of all, I will briefly introduce what analog multi-memory is. Then I will explain why AI chip needs analog multi-memory, its benefit, and the target market for edge AI chip application. Then third topic is how is eMemory's analog multi-memory IP, where I will show some key IP feature and the silicon data. Finally, I will summarize how to realize CIM on eMemory's analog multi-memory IP. Let's go to our first topic. What is analog multi-memory? If we want to develop an AI chip design, we must understand how it can be emulate the human brain. For example, you can see in this picture, this is the human brain, and there are many neural networks inside. Let's examine the primary neuron. It is one of the structure and the functional units of the nervous system. Neurons can perceive change in the environment and then transmit information to other neurons by current conduction. No matter what kind of neuron it is, it can be divided into 4 parts: receptive neuron, trigger neuron, conducting neuron, and upper neuron. So, the basic architecture of a neural network must include the input layer, hidden layer, and the output layer. It is a huge challenge to fulfill the behavior of a neuron, like voice, image recognition, and the inference. However, the massive breakthrough of REST AI moves processing from the cloud to the edge of the network. This is enabled by the technological innovation of AI algorithm. There will be many AI chip applications to demonstrate, like data inference, image, and voice recognition. In the future, human life will rely on this AI chip to accomplish many things, such as autonomous driving, cybersecurity, cloud computing, augmented reality, and big data servers. As you can tell, the functions of an AI chip are powerful. Move on, let's discuss how to fulfill neural network into the electronic level by the multi-layer perceptron structure. Here in this structure, we call it NLP, which include the input layer, hidden layer, and upper layer. They are all connected by synapses like weights. We can simplify this structure to many function blocks, like data input, weight, net input function, activation function, and output data. What is more, it can be compared to the multi-memory array architecture. We can see the data input is one data input. Weighting is the multi-memory unit. And the summation process is the multiple accumulate process. By being like this way, we call it MAC. It is the parallel computing operating to increase operating ability. The final step is to read out the analog current to identify what output data is. However, the bottleneck question is how to create an analog multi-memory unit to emulate the weight behavior. So the multi-memory cell shows the better data retention and persists different current level to adjust weight data. It is a big jump for AI chip. After understanding what analog multi-memory is, we should ask why AI chip needs analog multi-memory. Does it have any benefits? The AI chip design concept can answer this question. You can see in the picture A, which depicts the essential volume architecture for designing AI inference chip. Based on that, the fundamental component of the AI system is complicated and has higher power consumption due to the SRAM-based processing element. Maybe it is acceptable for cloud computing, but not for edge computing. For edge computing, we can consider change it to an in-memory computing architecture. This concept relies on analog multi-memory characteristics. It can simplify the original architecture to be more efficient and have a low power consumption. To compare the power of consumption between both, in-memory computing architecture is 10 to 1,000 times more inference energy saving than the conventional one. That's why AI chip needs analog multi-memory, especially in edge computing. In this slide, several applications are already to pay attention to, like smart home, automotive, and mobile. AI chips can be applied to family entertainment and security for the smart home through voice, video, and vision recognition. Real-time AI feedback is the fundamental function for this market. About automotive, ADAS, Advanced Drive Assistance System, must be multiple camera parallel processing to increase safe driving performance from level 2 to level 4 to realize truly count as autopilot. As to smartphone, AI chip must also maintain the quality of a picture or video and need a power saving function, which is very important for portable device. We believe they're just a part of the AI chip application. In the next generation, AI chip will help improve our quality of life. Next, we will introduce eMemory Analog Multi-Memory IP and let everyone understand this technology. Many memory types could be the candidate for AI chip, include runtime and the non-multi-type. Runtime memory include SRAM and DRAM, and the non-multi-memory include MRAM, IRAM, or no flash, NAND flash based, and the floating gate based. However, runtime memory is high power consumption, and the MRAM, IRAM is hard to control precision current. It's also from a flash-based memory that the fabrication process is more complex. So many papers and studies all reveal the floating gate base is the potential multi-memory for analog memory. Here, eMemory analog memory is a floating gate base, and it is based on logic process compatible embedding memory with one single poly process. It possesses stable program property by program verify function to have a multi-level serial current. so we can achieve excellent precision current controllability. In this platform, the IP also demonstrates good data retention property and the low error rate. In the next slide, I will show the more detailed IP feature for AP1. This slide shows the eMemory cooperated with the customer to develop a 3 megabit plus analog non-volatile memory in T-Foundry 55 IV process. The embedded floating gate non-volatile memory is without any extra mask. It also follows the foundry-based line process. Therefore, there are no issues impacting the process on this platform. The cell bit precision of the analog IP is 4-bit, has 16 levels of design, and can also achieve 5-bit, 32 levels, that depend on AI chip algorithm. In our CIM model, the power is 670 milliwatt per layer for one image, and its TOPS per watt is around 50. Our team builds an processor by floating gate-based non-volatile memory to emulate MLP and model the CIM with TensorFlow. In CIM application, it is important to control precision current well. eMemory's analog non-volatile memory has an excellent hierarchical current level with around 200 nanoamp per difference. Its standard deviation and the error rate are very, very low. Once correct enough silicon data with cell behavior, like a normal distribution or data retention, it could model the cell current to generate the cell model. This cell model will be provided for AI circuit simulation to obtain the optimization of weight. This advantage allows AI chip to have a high recognition accuracy and reasonable inference. Lastly, let us summarize the flow of realizing CIM on eMemory's analog non-volatile memory IP. The first step is to pick out the proper NVM model that rely on what kind of identifying object, like a simple number or a complete image. And then let software like the popular TensorFlow have built a new specific NVM model through Python for CIM as well as the training model in the AI chip architecture. Once we know the type of weighting, we can design our memory cell and the array to fit it with various degrees of accuracy, like 2-bit, 4-bit, or 5-bit. Finally, constructing the peripheral circuits. This may include persist, program verify, erase verify, activation function, precision ADC, and the DAC part, or something like that. This CIM flow is not one single way. We must collaborate with software and the hardware engineer to build a more effective flow in the next step. That is all for eMemory's webinar today. Thank you for your time to join us. We will open the Q&A section.
Hi everyone, thank you for joining this webinar. If you have any question, please kindly tap the Q&A chat box. I will answer your question after this speech. Thank you. Okay, Let me reply some question online for you. Someone asked one question. Is it MTP? And how is the endurance level? Yes, it's MTP, and it's based on our digital memory to develop to the multi-layer memory. So the endurance can achieve maybe 10 to 100. But if you want to use higher endurance level, maybe can achieve to 1K, 1,000, it should be okay. Okay, another question is this IP available now? This IP, we already cooperate with one customer to develop its SoC level. So we still wait SoC verification, but till now, I think it's very good now. So if the performance is very good, I will announce this SoC performance for everyone. Maybe next year. Thank you. And another question is, how about equipment computation resolution, same as the TensorFlow with a bar-bit fixed point? I think this question is very complicated because I know by our team member feedback and the AI algorithm is depend on many CNN model or RNN model, and this model the algorithm of a model can have a high resolution or high accuracy based on this model. So how to have a good computation resolution? I think the model is the major key, and if we have a good software and engineer to help us, I think it should be okay. But I think not limited any not limited any solution for it. So we just provide the memory storage to the weight and let the whole neural network can function in electronic level. So I think memory array structure is the key for analog IP. And we have a okay. We got another question. What is the maximum input number and the maximum output number? Okay, this IP, the maximum input allows 1,000 to 1,600 input, and the maximum output allows we can achieve 2,300 output. Another question is, learning algorithm can be run on chip. Yes, I think it depends on the algorithm, because if you have a simple algorithm, we can realize on the chip, and we can have the positive feedback and the negative feedback, and to revise the weighting number. We call rating ratio, and let to get a high accuracy. Okay, someone asked, what is the input and output bit precision? Okay, it's a good question. Based on our model, because we studied MNIST database and the fashion MNIST database, and we also studied C510. So, but because for the handwriting, I think I check my data later. Okay. Input precision is 1 bit because we use the binary, and the weight precision is 5 bit, and the output precision is 1 bit. Okay. Someone asked me, do you provide SW set as part of your IP? So the software, based on our software, our team is use the popular TensorFlow to build a model. So I think it's an open source and get it from the internet and many database. So it's very easy to get this resource from the online in or internet, any database. So it's no problem. But if you want to learn more how to use this software, and maybe we can have a more connection to understand it. Another question is, what accuracy can you achieve on CIFAR10, and what network architecture do you use? Do you obtain the number from the simulation or triple measurement? Okay, because CIFAR10, this data is very huge and the algorithm is very complicated. Our team is ongoing to quantize the weighting label and see how to implement to the hardware, because the hardware how to simplify the weighting and how to simplify the algorithm is very important. But for MIST and the function MIST, we get a very high accuracy, around the 95 or to 99 is possible. And till now, we don't have any real number from our chip. The number from the simulation and the chip measure. We have some chip measure data from the silicon, but it should be okay to achieve our simulation result. And I think it can achieve 4-bit precision and 5-bit precision. It is okay. But if you want get a high precision like 6-bit or like 6-bit, 8-bit, I think we must consider the top per wire. Like you have a very, very high bandwidth to tolerance any high precision, but you maybe need to consider the power consumption issue in your chip design. So it depends on the balance, depend on how to balance the power and the high accuracy. So I think it's a way we also suffer this checkpoint. Okay, I will reply the next question. What is the resistance range, namely mean and maximum resistance of a memristor? Okay, do you mean a benign loading or any resistance raise that like? Do you mean it or any loading issue in our chip level? If you mean it, I think it's also a very good question, because if you analog IP is very huge, the metal routing, the metal resistance is the issue, because the sensing current is very, very low. If you have a higher loading issue, the higher resistance in your IP, the accuracy will be affected. So input many sensing sensing part in the every memory block. It should be the solution for if you want to have high density weighting. Okay. Okay. Time's up. So thank you again for joining this webinar today. If you want to learn more details, welcome to connect directly with the account manager. See you next time. Bye-bye.